Solution of GATE questions. GATE EC questions on antenna array. So this one is the first question. In a uniform linear array, 4 isotropic radiating elements are spaced lambda by 4 apart. Progressive phase shift between the elements required. So we need to find out alpha. Progressive phase shift between elements required for forming the main beam at 60 degree of the end fire array. Means theta is 60 degree. Now we know that the normalized array factor for array of 4 elements, linear array, uniform linear array of 4 elements is sine 4 psi by 2 divided by 4 sine psi by 2. Now if I draw this array factor with respect to psi is the total phase difference, then it is something like this. At 0, the normalized array factor is maximum. And then first null occurs at pi by 2, second null at pi, and then 3 pi by 2. And this major lobe is maximum at 0 and 2 pi. Same is the case for negative side also. Now psi is total phase difference. And the psi is given by alpha, which is progressive phase shift between the elements, and beta d cos theta, and this beta d cos theta is phase difference due to the path difference. Now main beam means major lobe. Major lobe occurs at 60 degree. In terms of total phase difference, major lobe is maximum at psi 0, 2 pi minus 2 pi. So we will take psi 0. This alpha is unknown, beta is 2 pi by lambda, and the separation between the elements is lambda by 4 cos theta, and theta is 60 degree, so better to write cos 60. So this one is alpha plus pi by 2, and cos 60 is 1 by 2, which will give alpha minus pi by 4 radians. So the answer is C, minus pi by 4 radians. Now let's see the next question. Now let's see the third question. Two identical and parallel dipole antennas are kept apart by distance lambda by 4 in H plane. H plane means horizontal plane or XY plane also. They are fed with equal current, but rightmost antenna has phase shift of plus 90 degree. The radiation pattern is given by, and these are the four options. Okay. This is first antenna, second antenna. This angle is phi, and current here, the separation is lambda by 4. D is separated by distance lambda by 4. For first antenna, current is I naught e to the power j 0. For second antenna, current is I naught e to the power j pi by 2. So this alpha is pi by 2. Now, if I write the expression for total phase shift, then it is alpha plus beta d cos phi. So psi is 90 degree plus beta is 2 pi by lambda, d is lambda by 4 cos psi. So total phase shift is pi by 2 into 1 plus cos phi. Similarly, if I write the expression for normalized array factor, then it will be cos psi by 2. In terms of phi, it is cos pi by 4 plus pi by 4 cos phi. So if phi is 0, then the normalized array factor is, see, to draw the pattern, we take the magnitude of this. So when phi is 0, cos phi is 1, and this angle is 90 degree, cos 90 degree is 0. So this axis is x, y in all four options. And if phi is pi or 180 degree, then cos pi is minus 1, and pi by 4 minus pi by 4 is 0, so cos 0 is 1. And if normalized array factor is 1, that is maximum. Okay. So in C option, here phi is along x, positive x-axis, phi is 0, and in negative x-axis, phi is 180 degree. So when phi is 0, the field pattern is 0 because the array factor is 0, and when phi is pi, the field pattern is maximum because the array factor is maximum. So C is the correct option. So this is basically the case of cardioidal array. Now the next question is, a lambda by 2 dipole is kept horizontally at a height of lambda naught by 2 above the perfectly conducting infinite ground plane. The radiation pattern in the plane of dipole E looks approximately as, and these are the options. Okay. This is the perfectly conducting infinite ground plane. And this one is the antenna. at height of lambda naught by 2. Now there will be an image of this antenna at distance lambda naught by 2 below the perfectly conducting infinite ground plane. Now if both the antennas are fed with current of equal amplitude, for first antenna current is I0 e to the power j 0, then for second antenna the amplitude of current will be same but the direction will be opposite. So phase is minus pi, and total distance between the two antennas, actual antenna and the image, is lambda naught. So we can write the expression for total phase shift, that is psi, is alpha beta d cos theta. Suppose this one is z-axis. Phase difference in current is pi. Beta is 2 pi by lambda, and the separation d is, make it lambda naught. Lambda naught cos theta. So psi is pi plus two pi cos theta. Now the normalized array factor is cos psi by 2. So we will write normalized array factor in terms of theta, and it is cos pi by 2 plus 2 pi by 2 cos theta, which is cos pi by 2 plus pi cos theta, and normalized array factor is minus sine pi cos theta. And to draw the pattern, we will take the magnitude of this. So normalized array factor is sine pi cos theta. Now if theta is 0, theta 0 means along z axis, cos 0 is 1, sine pi is 0, so normalized array factor is 0. Now theta is 0 along z axis, and in z axis field pattern has to be 0 because normalized array factor is 0. So in option D it is non-zero, so the option D cannot be the answer. The field pattern is 0 in option A, B and C. So we have to choose the answer from first three options. Now let's take the another value of theta. If theta is 90 degree, theta 90 degree means along y-axis. Now what will be the value of normalized array factor? If theta is 90 degree, then cos 90 is 0, and sin 90, so in fact cos 90 is 0, so sin 0 is also 0. So along y-axis array factor, normalized array factor is 0, so field pattern has to be 0. So in C option it is along y-axis field pattern is non-zero, so this cannot be the answer. In option A, along y-axis field pattern is non-zero, so this is not the correct answer. So option B is the correct answer. Okay, and it is maximum, field pattern is maximum somewhere here. We can also find out the angle theta for this case. by equating the normalized array factor to unity. So this is sine pi cos theta 1, and sine pi cos theta is 1. So pi cos theta m is 90 degree. Okay, so cos theta m is 1 by 2, so this will give theta m as 60 degree. This is plus minus 90, so this is plus minus 60, or 60 and 120 degree. So this angle is 60 degree and this angle is 120 degree. So option B is the correct option. Now let's see the next question. Two half-wave dipole antennas placed as shown in figure are excited with sinusoidally varying of frequency 3 megahertz. Frequency is 3 megahertz, and the phase shift of 90 pi by 2 90 degree between them. The element at the origin leads in phase. Okay, so suppose current is I naught e to the power minus pi by 2. So for the second antenna, current will be I naught e to the power j 0. It means if I move from antenna at the origin to next antenna, the progressive phase difference will be minus 90 degree. If it is minus progressive phase difference, no, the element at the origin leads in phase. Sorry, this should be plus. Or better to write plus pi by 2. Okay, so if I move from antenna at the origin to the next antenna, the progressive phase difference will be minus pi by 2. Alpha is minus pi by 2. If the maximum radiated E field at the point P in xy plane occurs at azimuthal angle 60 degree, this angle is 60 degree. Phi is phi angle from x-axis is 60 degree. Then what should be the distance between the two antennas? Now we know that the total phase difference psi is alpha plus beta d cos phi, and alpha is minus pi by 2, and beta is 2 pi by lambda, d is unknown, and cos phi is 60 degree. So maximum of E field occurs at psi 0. Cos 60 is 1 by 2. So 1 by 2 is d by lambda, or d is lambda by 2. Now lambda is c by f, and this c is velocity of light 3 into 10 to the power 8 divided by 2. F is 3 into 10 to the power 6, 3 megahertz. So d is 100 by 2, that is 50 meters. So separation between the antennas is 50 meters. Now why psi is 0 here? Because we know that the normalized array factor for two antennas is cos psi by 2 or sine 2 psi by 2 by 2 sine psi by 2. If I draw the magnitude of this normalized array factor with respect to total phase difference psi, then it is something like this. There is no minor lobe, just major lobe, and major lobe is maximum at 0, 2 pi, minus 2 pi, and nulls occur at pi, minus pi, and so on. So we have made size 0 for maximum E field. That's why psi is 0 here, and this will give distance 50 meters. Now the next question is sixth question. The directivity of antenna array can be increased. It can be increased by adding more antenna elements. Okay. As larger the number of elements, what should be the correct option? Improves the radiation efficiency, increases the effective area of antenna, results in better impedance matching, allows more power to be transmitted by antenna. See, directivity of antenna is increased by increasing the more number of antenna elements. So directivity is increased. Now we have the direct relation between directivity and the effective area of antenna. Effective area of antenna is denoted by AE. This is d lambda square divided by 4 pi. So effective area of antenna is proportional to d. I'll derive the expression for effective area in some other lecture. Right now I am using it directly. So effective area of antenna is proportional to d. So if d increases, effective area also goes up. So I think B option is the correct option. Question: half a dipole antenna is kept in XY plane and the oriented along 45 degree from x-axis. We have to determine the direction of null in the radiation pattern for phi 0 to 180 degree or pi. Here angle theta is varying from 0 to pi is measured from z-axis, which is quite obvious, and the angle phi varying from 0 to 2 pi, which is measured from x-axis in xy plane. That is also true. Now we know that if we have a single dipole antenna, then direction of maximum radiation is perpendicular to antenna axis, and direction of minimum radiation or null is along the antenna axis. If the antenna is located along z-axis, then this will be, z-axis is the antenna axis, and the nulls occur at theta 0 and the maximum radiation occurs at theta 90 degree. Okay, so the unit pattern or E field depends on sin theta here. Similarly, if it is in ZX plane, if antenna is located along Z-axis and this x-axis is the antenna axis, Then for theta 90 degree, radiation is minimum, and for theta 0 radiation is maximum. So the unit pattern E theta phi depends on cos theta. If cos theta is 90 degree, E is 0, and if cos theta is 0, E is maximum. Similarly, in xy plane, if antenna is located along x-axis, then x-axis is the antenna axis, and for phi 0 we obtain the null, and for phi 90 degree the radiation is maximum. So now the unit pattern depends on sin phi, because phi 0, E is 0, phi is 90 degree, E is maximum, and if antenna is located along y-axis, then this one is the antenna axis, and unit pattern depends on cos phi. When phi is 0, cos phi is maximum, which is perpendicular to the antenna axis, and when phi is 90 degree, cos phi is 0, or field pattern is 0 along the antenna axis. Now for the given case, in the question, antenna is located at an angle 45 degree from x-axis. So this one is the antenna axis, and field should be minimum or 0 along the antenna axis, where phi is 45 degree. And in xy plane, suppose this is x-axis, y-axis and z-axis. In xy plane, theta, which is measured from z-axis, is always 90 degree. So when theta is 90 degree, phi is 45 degree, the field pattern is minimum. So option A is the correct option. If I have to write the expression for the unit pattern E theta phi for the given case, E theta phi should be proportional to sine phi minus 45 degree. So when phi is 45 degree, sine 0 is 0, or we can write cos phi plus 45 degree. When phi is 45, cos 45 plus 45, 90 degree, or field pattern is 0 or null occurs. So these are the questions of GATE exam from the chapter antenna array.